For introduction, traffic flow is an important area of study in mathematics and transportation engineering. It examines the interaction between road users such as pedestrians, cyclists, and drivers, as well as the transportation and also infrastructure, including roads, traffic signs, and traffic control systems. The main objective is to understand and develop an efficient transportation network that ensures smooth traffic movement while minimizing traffic congestion problems. Traffic flow can be analyzed and predicted using systems of linear equations from linear algebra. In a network of one-way streets, these equations can help determine the optimal number of vehicles that should travel through each road segment to reduce traffic congestions. The information gathered from traffic flow analysis is useful for transportation engineers as it helps them optimize traffic signal timings and evaluate the impact of vehicle usage on road surface conditions. In this study, the Gauss-Jordan Elimination method is used to solve the system of linear equations representing the traffic network. This method provides a systematic way to determine unknown traffic flow rates and improve traffic management decisions.
Purpose of study. The first one is to solve traffic problems using linear algebra to find ways to reduce heavy traffic jams in growing cities. The second one is to calculate traffic flow at intersection, creating a simple math equation to balance the number of cars entering and leaving an intersection to prevent traffic jams. The third one is to find missing traffic data using the Gauss-Jordan Elimination method to calculate and recover lost traffic data along roads with traffic jam. And the last one is to manage vehicle limits, determining the minimum and maximum number of cars allowed on one-way street to keep vehicle moving and avoid traffic.
For our methodology, we are analyzing a downtown grid optimization problem across 4 one-way intersections A, B, C, and D. Our goal is to balance the grid and find the unknown traffic volumes on our internal roads X1, X2, X3, and X4. To find the missing data, we use the principle of flow conservation, where the traffic entering an intersection must equal to traffic leaving it. By analyzing each intersection, we generate a system of 4 linear equations. For intersection A, 300 cars enter from the outside and they leave through X1 and X2, giving us X1 plus X2 equal to 300. For intersection B, traffic enters from X1 and leave through X3 and external axis of 200, giving us X1 minus X3 equal to 200. For intersection C, traffic enters from X2 and X4 and leave through an external axis of 200, giving us X2 plus X4 equal to 200. Finally, for intersection D, traffic enters from the outside 100 plus X3 and leave through X4, giving us X3 minus X4 equal to negative 100. Next, we take this equation and load them into augmented matrix. To solve our unknown values, we use the Gauss-Jordan Elimination method to reduce the matrix down to reduce row echelon form or RF. As you can see through our row reduction, our final row cancel out entirely to all zeros. This means our system has a dependent structure with infinite possibilities, making X4 our free variables. Rewrite our final RF matrix back into algebra term, giving us our general solution, which is S4 equal to S, where S is all real number, S1 equal to 100 plus S, x2 equal to 200 minus S, and x3 equal to minus 100 plus S. Our final step is to determine the minimum and maximum vehicle limits to keep traffic moving. Because this is a real-world one-way street system, traffic flow cannot be negative. Therefore, every street values must be greater than or equal to 0. Looking at x3, which is negative 100 plus S, the value of S must be at least 100 so that x3 stay positive. Looking at x2, which is 200 minus S, the value of S cannot be greater than 200 or x2 becomes negative. We can conclude that S must be greater than or equal to 100 and S should be less than or equal to 200.
We will continue with the discussion of the result that my friend get after apply Gauss-Jordan elimination to the equation of our traffic flow. As stated from my friend, the result of the unknown traffic volume x1, x2, x3, and x4 in a one-way street network are x1 equal 100 plus S, x2 equals 200 minus S, x3 equals to minus 100 plus S, x4 equals to S as any real number. From this data, we know that this augmented matrix have an infinite solution. However, since this data is from one-way traffic flow, the traffic volume cannot be negative as stated from my friend. Therefore, every street value must be greater than or equal to 0. As stated previously, the value of S must be greater or equal to 100 and less than or equal to 200. Why? Because when the value exceeds or doesn't meet the requirement of the S value, then one of the street value will become negative. Again, the data will not be valid as it defies the logic of the traffic flow. Now, by using 100, the minimum requirement for the value, and 200, the maximum requirement value, and applying it into our street value, we will get S1 equals to 200 minimum and 300 maximum. X2, we will get 100 minimum and 0 maximum. X3, 0 minimum and 100 maximum. X4 is 100 minimum and 200 maximum. For the X1, this street is the most critical point in the entire network of traffic flow. The number of vehicles per hour show us that this street must be prioritized to ensure it will never disrupt the smoothness of the traffic flow. Now onto the X2 and X3. These two streets is the most flexible as one of the street value can drop to 0 depending on the parameters value of S. Therefore, closing one of the street, for example, for maintenance purpose, will not directly disrupt the traffic flow as the traffic can naturally reroute. For X4, since the value of the street X4 directly holds the value of our parameter S, controlling the traffic light synchronization at intersection D will automatically allow us to directly balance our traffic flow network. In conclusion, this study shows us that linear algebra and Gauss-Jordan elimination method can be used to solve real-world traffic problems. By setting up traffic intersection as linear equation and using matrix operation, we were able to successfully find missing traffic data and calculate the minimum and maximum number of cars that allow in certain route. This method helps traffic engineer better manage vehicle flow, set up traffic light accurately, and reduce heavy toll congestion. Ultimately, it proves that mathematics is a practical and powerful tool for making city roads better and safer.